Hello Year 12, and welcome to our video on intermolecular forces, which I've subtitled When Atoms Have Long-Distance Relationships, though that might more accurately be written When Atoms or Molecules Have Long-Distance Relationships. This is going to be quite a short video, there's only a couple of specification points, but I really want to make sure that we've got a firm understanding in the base principles of this. I will be testing this in the lessons, we'll probably do a little bit of extended writing on this. So make sure you've done some nice summaries, some detailed Q questions that you've really thought about. Go for the hows and the whys rather than the whats. So these are our specification points. They are 3 in number, and they are relatively simple. However, the questions that tend to be asked about this require you to apply the ideas in an unfamiliar context usually. Okay, so intermolecular forces. In this picture we've got a nice spherical droplet of water. But have you ever wondered why water is a liquid, why things can skate on top of it, and why it clumps together in drops rather than spreading out as individual atoms when it's running down a window? Well, the forces between molecules are giving water its properties, and there's 3 sorts of intermolecular forces we're going to be learning about today. Hydrogen bonding, or H bonding, is the first one. You've probably heard of that one from GCSE and from biology. There's dipole-dipole interactions, and there's van der Waals forces. Now, all of these forces are weak compared to covalent bonds. These are forces between molecules, okay? I've defined them as intermolecular forces, the long-range interactions between the molecules. These aren't bonds, despite what hydrogen bonds might be called. They are forces, they're interactions, they're what's keeping the molecules close together. That's what's stopping them from repelling each other. Okay, so let's start with hydrogen bonding. There are 2 things you need for, this is the strongest of all the intermolecular forces, and that gives out some properties that we're going to be talking about in a second. And there's 2 things you need for it. A hydrogen that's bonded to an electronegative atom on one molecule, and then on the other molecule you need a lone pair. So for example, on all of these molecules we could have hydrogen bonding because we've got lone pairs and hydrogens bonded to electronegative atoms. So this is some hydrogen bonding in action. You always draw hydrogen bonds as these kind of flat dashed lines, and you should always draw on the partial charges when you are doing a diagram showing some hydrogen bonding, because this bond works, this interaction works based on the fact that all of the electrons pretty much are being pulled off of the hydrogen, and that the oxygen has this lone pair it can pop in there. It's somewhere between an intermolecular force and a dative covalent bond. It's a very, very strong intermolecular force, and that gives rise to a couple of wacky properties that water has. For example, water has a very high boiling and melting point relative to other similar simple molecular compounds like hydrogen sulfide, which is a gas at room temperature. This is because of the strong hydrogen bonds between each molecule. The other thing is that liquid water is more dense than solid water, and this doesn't make any sense, because if you think about the particle model of a solid and a liquid, there is no way that this liquid is going to be more dense than this solid. There's big gaps between all the molecules here, whereas here they're ordered and packed nice and close and tight to each other. This should be more dense. However, this is what happens with water. When water is frozen as ice, it spaces itself so as to form little hexagons of the most hydrogen bonds possible. So you can see that each oxygen is forming each water is forming 2 hydrogen bonds from its hydrogens and 1 from its oxygen. So it's each forming 3 bonds. So it forms this big sort of crystalline structure, all spaced out to get the most out of it. But in liquid water, the hydrogen bonds are constantly breaking and reforming. So we end up with a much more closely packed arrangement, making the most of this V shape. And that is why ice floats on top of water. Okay, that's hydrogen bonding done. Dipole-dipole interactions are very, very similar. It's the next strongest after hydrogen bonds, and they're kind of the next step down. Here we have 2 polar molecules, so for example HCl, which I've drawn here, and while the hydrogen or other atom has not had quite enough of its charge pulled off it to be able to have a kind of semi-dative covalent bond, we have got quite a strong bond. However, if you think about it, hydrogen chloride is a gas at room temperature, so it's obviously not as strong as hydrogen bonds. These strong bonds aren't as strong. It's an electrostatic interaction between this partial positive and partial negative charge, if you want a really fancy definition. Finally, we have the most complicated and weakest van der Waals forces. So this is what happens. Let's imagine these two atoms here. These could be atoms or these could be molecules that are homogeneous. Remember, homogeneous means same charge everywhere. So it could be a Br2 atom, it could be a xenon atom, just anything with a homogeneous charge. Now, these shouldn't be attracted to each other. They should just be completely nothing to each other. If they got too close, their electrons would bump each other off, but that would be it. However, the electrons are in this sort of probabilistic cloud, and sometimes there's going to be more electrons on one side of the molecule or the atom than there are on the other. That's going to give you a partial charge on one side, on both sides. So we've got a partial positive charge developed here, and a partial negative charge over here, where all the electrons have ended up. Now this then affects our other atom. This partial positive charge is going to pull all the electrons towards it, and the partial making a partial positive charge on the other side, and this will do the same to another atom, so they'll stick together for a short time. These forces are incredibly weak and they rely on probability. If you would like to see an animation of this working in sort of in real time, I'm going to put a link in the text underneath the video. Okay, that's everything we need to know about intermolecular forces. You need to be ready to be able to apply these ideas by the lesson on Wednesday, so make sure you've thought about them deeply. Thanks very much.